So we know the basics of an alternator's construction and operation, but do we have a strong grasp of voltage regulation and rectification? The vehicle's alternator produces enough energy to meet the electrical demands of the vehicle. The output from the alternator's B positive terminal is rectified to DC and regulated to a predetermined voltage. Rectification is the process of converting alternating current into direct current. A vehicle's alternator uses a diode bridge to perform this task. Each end of the alternator's star or Y winding, or each junction of a delta winding, is attached to the diode bridge. The bridge in conventional alternators is made up of 3 positive and 3 negative biased diodes, so each phase winding uses 1 pair. The 3 positive biased diodes prevent the flow of current from B positive or the vehicle's battery to ground. To understand full wave rectification in an alternator, we need to take into account current flow through Y and delta windings. Let's take this one step at a time and look at the current flow through each leg of the Y stator as influenced by the rotor's north pole. Each circuit in a Y or star type stator is made up of 2 legs connected in series. When a pair of windings is used to generate current flow, the third winding or leg is said to be neutral. Since each winding is separated by 120 degrees of rotation, current flow through each begins about 60 degrees before the leg to 60 degrees after. As the rotor's north pole approaches coil A, positive current is induced in the coil and travels to diode pair A. Current can only travel through the positive bias diode to the B positive terminal, as it is blocked by the negative. All circuits need a ground path, and stator coils are no different. The ground path for coil A is via ground point B, through the negative bias diode, then stator coil B, where it meets stator coil A at the star point. This circuit creates a positive analog voltage every time the north pole of our rotor passes this leg. Current is induced in coil B in the same fashion as A. At 60 degrees before leg B, current is induced in the circuit. The current reaches its peak when the rotor's north pole flux cannot move any further across the coil winding, or the rotor pole is at its closest point. Further rotation of the rotor decreases current flow, and so the voltage drops to 0. Current flow through the circuit begins at coil B, then flows to diode pair B. Current is blocked by the negative bias diode, so it can only flow through the positive diode to the B plus terminal. Leg B's return circuit is from ground point C, through negative diode C, then on to stator coil C, then the star point, where it completes the circuit at stator coil B. As the rotor reaches about 60 degrees before leg C, current begins to flow from this stator coil. The current flow for this leg continues on to diode pair C, where it can only flow to B positive as it's again blocked by the negative biased diode. The return path is via ground point A, then negative diode A. Current travels through stator winding A, then meets leg C at the star point, completing the circuit. Now that we understand how the rotor's north pole influences positive current flow, let's have a look at the effect of the south pole on the same windings. While the north pole influences stator coil A, the rotor's south pole begins to induce current flow in coil C. Due to the laws of magnetic induction, this magnetic field will now induce current flow in the opposite direction. When the rotor passes a point at about 60 degrees before leg C, current flows from ground point C via the negative bias diode, through coil C, then the star point, through coil A and onto diode pair A, past the positive diode, then to B+. This movement of the rotor creates a negative current in coil C, but due to the series connection and diode bridge, the current is routed through coil A and onto the battery as a positive flow. The rotor's south pole is inducing negative current flow in coil A, just as the North Pole finishes its induction of coil B. Flow at this stage begins at ground point A, through the negative diode, coil A, junction point, coil B, the positive diode, then battery positive. Again, the current captured is DC at this point. The next coil to be induced by the stator's south pole is B. Current flow begins at ground point B, flows through the negative diode, onto coil B, past the junction point, through coil C, onward to diode pair C, and then to battery positive. If we look at current flow from each of the stator coils, we can see the familiar AC waveform with each signal separated by 120 degrees. But if we look at the waveform after rectification, we can see each negative cycle has been reversed due to the diode bridge. Full wave rectification has effectively recovered energy that would otherwise be lost. We should note that an alternator's rotor may have up to 14 poles, 7 positive and 7 negative. So this equates to 14 positive and negative cycles per stator leg per rotation. Once rectified, the negative portion of the cycle is reversed and captured, so the analogue DC signal at B positive looks like this. The portion we see on an oscilloscope is known as the ripple voltage. A stator that is delta wound has each of its legs connected in parallel. The junction of each is connected to a pair of diodes mounted in the rectifier bridge. In this design, we can see that as the rotor's north pole passes coil A, current flows from the AB junction to the diode pair, where it continues on to battery positive. Again, the current is prevented from travelling to ground due to the negative bias diode. The ground circuit is formed through diode pair 3, then to the coil AC junction. We can see coil B and C are inactive or in a neutral state. Continued clockwise rotation now allows the rotor's south pole to influence coil C. This induces current flow in an opposite direction, which then flows to the next diode pair. Only the positive current can pass this diode and travel to battery positive, with the ground circuit flowing through diode pair 3. This same action of forward and reverse current flow through each stator coil is fed to the rectifier bridge for conversion to direct current using a combination of diodes and ground paths. Like the star or Y design alternator, there are many north-south fields in the rotor, increasing the current flow available from the stator. A sound knowledge of AC rectification moves us one step closer to understanding inverter technology used in electric vehicles. Keep watching this series for more training on voltage regulation. See you next time.